Welcome, ladies and gentlemen, to this video lecture. Okay, so now we come to what is called the fundamental theorem of algebra. And what does this say? It says any polynomial over C has at least one root in C. So let us have that sink in. Every polynomial over C has at least one root in C. This is not true if we replace this last phrase, at least one root in C, with one root in R. So for example, the following polynomial has no root in R. So this is not true if we replace the complex numbers by the real numbers. And this is one reason for the existence of complex numbers, is the elegance of the fundamental theorem of algebra. It says every polynomial in over C has at least one root in C. And there's something that I forgot to add. Let f be a polynomial over C with degree of f of x greater or equal to 1. So every non-constant polynomial in over C has at least one root. So of course, if you have a constant polynomial, let's say constant polynomial I, if it's just constant, then it has no root. So the degree must be greater or equal to 1. And again, let me reiterate, this does not work if you restrict your view to roots being in R. There's a consequence of this theorem which is very useful, and that is the following theorem. So you can use the fundamental theorem of algebra to prove the following theorem. So every polynomial over C of degree n, and n greater than 1, has exactly n roots. And I'm going to put here in brackets counted with multiplicity. Some of them might occur multiply. So counted with multiplicity. And this is a consequence of the fundamental theorem of algebra. So, what does this theorem say? It says, doesn't matter what polynomial you take, you know exactly how many roots it has, if you count them with multiplicity. So, for example, you just write down a random polynomial, like the following: I x to the 5 plus 3 plus 2i over x to the 4 plus square root of 7i x cubed plus 3x squared minus 19x plus 1. So this horrible polynomial, we can immediately say has 5 roots, because its degree is exactly 5. Some of them might occur multiply, so 5 roots, and let's add here counted with multiplicity. And if we know this polynomial has 5 roots, we can go look for them, and once we have found 5 of them, we know exactly that we have found all 5 of them. So this it doesn't quite give us a method of finding them, but it tells us how many there are. So if we find 5 of them, then we know that we have all of them. So this is the power of this theorem, and also is displays the elegance of considering polynomials over C and looking for the roots of polynomials over the roots of let's say the complex roots of polynomials, instead of restricting one's view to the real numbers. Okay, and in the next couple of videos we will look at strategies for finding the roots of polynomials, and we will look at a couple of examples. I will see you in the next videos.